This here is our computational thinking with data science final project on construction strength. Construction strength. I am Kaden
Concrete.
Johannes. Concrete strength. I am Kaden Johannes. That is
Evan Mason. All right, going over our literature scan of concrete. Concrete is a mixture of many different substances, which all of them have different impacts on strength, which is why there's so many variables in calculating the concrete strength. Particularly like whenever having like your binding agent, the amount of binding agent per like a pound of concrete or whatever, um, can greatly change what its compressive strength is and how just strong in general it is, how resistant it is to weathering, um, and which is why using data is way much more better because we can calculate a predicted strength without having to deal with trial and erroring multiple different types of mixtures until we just happen to find the strongest mixture whenever we can use data to test hypothetical mixtures before going into creating a real one.
in this cell we import all of our notebooks. That way we can run our code how we need to. The most important ones are the statistical ones like stats models.
Squaring. Squaring's good for like the uh, generating the like linear regression train models. Here we're gonna import and read the CSV file, including all of our data on concrete. We're gonna store that in a variable called concrete_df. Then we're gonna rename the columns because the columns in the original data are a little long and not as pretty to look at. And so we're gonna change to being more organized and easier to read.
This here is all of our data in the CSV file.
We're gonna print out the info on the data, not necessarily the data in it, but the way it's stored in the data frame itself. And then we're also gonna print basic statistics using the describe function. We can see like we have the mean, the standard deviation, and all that for every single column in the data frame.
This here is a pair plot of our data. It's basically just a table of plots, and it shows the correlation between different things that go into the mix of concrete, like cement and slag and stuff. But that was kind of ugly, so we made it prettier in a heat map. This just puts it in numbers, and the most important thing for us is the strength of the concrete. And as you can see here, the age, the plasticizer, and the cement.
It was slag.
It's like, no, it's cement. Cement's highest number. It's the three highest
Oh,
numbers.
sorry, yeah. Sorry, my bad.
Yeah, no.
Cement, plasticizer.
So those are the most important for us, and they will help us kind of get our calculation and be able to predict whether the cement will be strong or weak.
Because since we found our top three most significant factors, we separate those into its own columns, which is cement, plasticizer, and age. Then, using those, we create a train model and a linear regression model and a prediction model using the train model. For those featured columns. Here we have an actual versus predicted relationship between for those featured columns. Then this one, another value. This one using the actually can't tell, but going on.
Okay. And using those, we predict we get the R squared score, which is the most important thing whenever it comes to calculating the strength of our concrete. Here we made a power law model. Basically, it shows the exact same thing as the last one. It's a different way of putting it, and the numbers be be more will be further apart or closer together and have less variation depending on what model we use. So using that one, we get an R score of 0.2228, which is very low and not very good. So we will not be using this model. This here is an exponential model. It's another way of displaying our data. It gives us a R score of 0.447, which is the second highest, which means we will not be using this one, but it is actually a pretty good method. So here we compare our models, and as you can see, the best model for us is the multiple linear regression one because it has the highest R squared number.
Here is where we actually start our interface. So first we're going to ask our user, how many samples do you want? How many of these concrete samples do you want to try? So for this example, we already did it because just so we have an easy presentation. The number of samples we're going to do for this is 1. So now we input how much the cement superplasticizer and age of our hypothetical sample, and we only do it once. If we were doing 2 samples though, when we input it, we put a space between them, and then using a strip and split function, turn it into 2. But for this, we're just doing 1. And then that will give us a predicted strength of, for this one, which is all numbers of 23, it's 35.96 megapascals. Now here, this is just doing.
This is the predictive strength of our sample that you gave us. As you can see right here, the predictive strength of them. The best model or the best prediction of the sample you gave us is number 5. It is predicted to be able to hold way more than the other one. This here we are updating our database. So if someone were to find new concrete mix and they're like, oh crap, I need to add this to our data, they'll use this. So here we ask them for the number of new observations, and then we give them an interface to, we've already filled this out, but we ask them for new observations, they give us 2, and then in the next cell, we ask them for the data. So as you can see, as he said earlier, as Evan said earlier, you separate them by space, and that's all you need to do to separate between 2 different models. And in doing that, and putting in the information for all of them, it gives us the strength of the samples that you found.
Yes, as you see in these 2 hypothetical samples, we actually see that sample 2 is stronger than sample 1. This is just displaying our new data that has been added to the data frame.
Yeah.
This is our updated R score. It's just doing the stuff that we did originally with the first data frame with now the new data frame.
Yeah. Then this here is the final model of our new data frame with the 2 added samples. And then that is what the user will see. And that's our project.
Thank you for watching. Put a lot of work into this. Even with all the finals and stuff, we managed to get this together. So I really appreciate it.
Thank you for the semester. It was a lot of fun having your class.
That's true. Learning a whole new language, basically. You have a great day. Bye.